Hi everyone, welcome to the week eight of this tutorial sessions of this course Sobolev Space and Partial Differential Equations. Hi there, my name is Shammi and I am a research scholar at IIT Delhi. So in this week, in the video lectures, you have studied about continued about the trace theory, that how we can define a notion of values of the function in the Sobolev spaces at the boundary. And after defining that trace theory, we have we have developed the theory of this abstract variation problems. So these variation problems are the key to which basically these Sobolev spaces are constructed. So like these are the variation problems. So basically the idea is that we considered a partial differential equation. And what we try to do, we try to convert that solutions of the partial differential equation to a functional, and then that functional is on a hill on a space, and that space is actually naturally can be seen as a Sobolev space, and we try to minimize that's a function on the Sobolev space, and the critical points of that function are nothing but the weak solutions of our partial differential equations. So it's like a transforming or translating the problem from solving a PD to finding the critical points of a functional on a Sobolev space, and that function is not necessarily to be linear. So that's the idea, and that's what we saw in the video lectures. So we are finally interested in uh, solving problems which can be like not all problems can be translated into this variational setup. Some problems, but largely problems can be transformed into variational setup. And the main advantage is that the mostly the problems which we encounter in physics or any uh, in general application purpose, they can be translated into the variation setup. So it's quite a rich domain, and many problems can be tackled which arise in physical nature. So we have so uh, this is a quite rich theory. So it's and also not that hard. We see the one of the most fundamental lemma or the theorem to solve the problems variation to solve the main of these variation problems, and that is the Lax-Milgram lemma. So we will see some questions based on the Lax-Milgram lemma mainly, and before that we will let us continue some of the things which we know about the Sobolev spaces and about the trace theory. So let's start the question with that, and then we'll finally do some questions based on the Lax-Milgram lemma. Okay, so the first question which I would like to do today is about the question which is based on the which is based on the Sobolev spaces which we defined as hyperfourier transformation. So last time we did, so it's all about the Sobolev space HSRN where S is greater than n by 2. Last time we did this for these spaces. These spaces are continuously married into the L infinity space. So they are in L infinity, but there's something more which we can deduce from that. We can in fact show that this HS space is turns out to be an algebra. What do I mean by algebra? I can define a notion of product there, such that if I take U and V in HS, then the product is again will be in HS. So the question is the following, that show that if U and V belongs to HS of Rn or S greater than n by 2, then UV product is also in HS Rn. And what also we have this UV, the HS Rn, is less than or equal to some constant time, the hs norm of u, and some hs norm of v. Moreover, the constant c, depending only on s and n. Solution. So this is something which, in fact, this says that this is an algebra. So one thing which we would like to use here is that so the hf Rn is nothing but all those functions in L2 Rn is that 1 plus mod xi square whole is for s by 2 into u hat. This has to be in L2 of Rn. So this is the space, the equivalent definition for this space. And one more thing which you would like to use is that the if we take u and v, and if I take the Fourier transformation of u and v, and then this is actually nothing but the Fourier transformation of u convolute with the Fourier transformation of v. So this is actually the result we have here, and this holds for all u and v in, let's say, in a good domain, let's say in L2, but yeah, we can have this result. And also one more thing which I like to point out, this equality is sometimes people denote by equal to this time some constant factor, and constant factor is something 2 pi raised to power of n by 2, but that comes if we take different definition of Fourier transformation. So this varies from the definition. If they are like generally two definitions of Fourier transformation, if you consider another one, you will get the another another version of this equality. But ultimately, it's like they are equivalent up to a constant factor. So one more thing which we would like to use is this we have 1 plus mod xi square whole raised to power of s by 2. So something they have a convolution, so uh, we have to somehow consider that thing and somehow deal with that thing in a way that it helps in our convolution purposes. So I just consider 1 plus mod xi square whole is for s by 2. So with help of the triangle inequality, what can I write this? I can write this as 1 plus mod xi minus n plus psi minus eta whole square whole is for s by 2. So I can write this, and then by triangle inequality, this whole can be written as 1 plus 2 times mod xi minus eta whole square plus twice of square whole square of s by 2. So this is again by triangle inequality, and then we use the AMGM there. So next, so not AMGM, I'm just using the triangle inequality, that is enough, and then we are squaring the thing, and then squaring, and then AMGM again. So that's how we're getting this. And finally, we want now we have this xi minus eta and eta in a place, and now how can I ultimately want this 1 plus eta square and mod eta square, and then 1 plus modulus of xi minus eta square. to be in place. So if we do some calculations, so this actually will be less than 2 raised power of s whole 1 plus mod xi minus eta whole square whole raised power s by 2 plus 1 upon 1 plus mod eta square whole raised power of s by 2. So we can prove this, and then finally we have considered this thing here, that if you consider uv hs norm square, so this is nothing but the integration of Rn 1 plus mod xi square whole is power of s, and then we have uv whole hat xi square d xi. So now we're using this result, that whole thing uv hat can be written as u hat convolution v convolution, and this whole thing at psi whole square dz. So that I know. And then next we would like to use this some constant time. We have this like on the constant, but whole is for Rn. This 1 plus mod, so it's whole integration of over Rn. So I'm just taking the, so let me write in a better way first. Whole Rn 1 plus mod xi square s by 2, and this is actually this, and then we have this mod of u hat psi minus eta into v eta at eta, v hat at eta, and this modulus d eta, and then whole square d psi. So what I did here is just I just consider this 1 plus mod xi square whole square s by 2, the whole square, and then I just took the whole square outside and then is opened the convolution. So I applied definition convolution at xi, and next I will use this expansion which we did, that this inequality. So this c will be some another c, so let's say c1. So this will be 1 plus mod psi minus eta whole square whole square of s by 2, and then we have plus 1 plus mod eta whole square whole square of s by 2, and then we have mod u hat psi minus eta into mod of v hat at eta, and then we have d eta whole square d eta, and then we can take this to be less than equal to, so I cannot less than just equal to, so just distributing 1 plus mod xi minus eta whole square whole square s by 2, u hat xi minus eta do v hat eta then plus again integration of Rn 1 plus mod eta square whole square of s by 2 mod u hat psi minus eta 2 mod v hat eta and then we have this d eta and then we have finally whole square and d psi. So finally, what we can do now, you can use again this x, uh, open the square and then again applying the ANGM. So this will be 2 of C1, but I can write this as C2 of all Rn and then Rn again. And then first thing I have square of this thing. So this is 1 plus mod xi minus eta whole square of s by 2 u hat mod xi minus eta. And then we have this v hat eta d eta whole square plus again we have Rn, another Rn, 1 plus mod eta square whole square s by 2 u hat xi minus n eta v hat eta d eta whole square d xi. And then we have this thing. So d eta is also here. And now what we try to do, we will use this Cauchy's cos inequality here. But before that, using the Cauchy's cos, we can observe one more thing. And this thing is nothing but C2 integration of all of Rn. And now if you observe this is a convolution of this is a convolution of 1 plus so this is a convolution of 1 plus let's say mod x square whole square of s by 2 mod u hat at x convoluted with v hat mod at x. This we are evaluating it psi, right? And this is a whole square of this thing psi, right? We have this thing, and finally, similarly, we can do the same thing here. So this is again Rn, and then this time a convolution of u hat convoluted with 1 plus mod x square whole square s by 2 v hat x whole at xi, and this as a whole square d psi. So this whole can be convolution in terms of this thing. And finally, what we would like to use is the Young inequality here. Then by the Young's inequality, we have, so you want to see inequality that have convolution G, LP has to be less than equal to some constant times the LP norm of F times the L1 norm of F. So this is less than equal to some C3 times. So when I apply the Young's inequality, so what we basically take P, we take P equal to 2 here. So this will give me, when I apply, this will give me the HS norm of my U when I apply the L2 norm here. So this will give me L2 norm of this, but that is the HS norm of U only. And I will take L1 norm here. So by Young's inequality, I have this thing, the integration of, so just the right directly, this is nothing but the uh, HS norm of U. And then we have this integration of Rn of mod V hat psi d psi plus the same thing goes here. It will be a HS norm of V here. And then we have integration of Rn of U hat xi mod t xi. And if you observe closely, this is something this is something which we did in the last tutorial, that this whole thing is actually again bound when my, since s is, so this is nothing but V at 0 only, and this is nothing but equal to U at 0 only. But since s is greater than n by 2, we know that the HSRN is continuously embedded in the L infinity of Rn. So this is something which we know. So what we basically end up, this is less than equal to some C3. It's like we can take another constant C4. U of HSRN. And then since this is V0, so V0 is less than equal to the L infinite norm of V0. And eventually this will give you some V times HS norm of Rn. The same thing goes with the right the another term. And what we can do finally, we can take this will do twice of the HS norm of U times the HS norm of V. And after that we can take a constant to be outside. So ultimately, what do we end up here with the HS norm of U times the HS norm of V? Thus, we have and one more thing. So this will actually not HS norm. This will be square of HS norm. Why? So why is that the case? That is because I am taking the L2 norm here. So it will be actually, so it's actually it's just an integration. So it will be H2 if I'm getting a P norm here. So it will be a P here and P here as well. So it will be actually square here and also a square here, square here, so a square here. So this will give me a square and square here. So this will give me the HS norm of Rn Question some constant time, the HS of R, the U, HS now of U, and then the HS now of this. Okay, so far so good. So that's how you prove. And that does not require the density account. You can directly start with this U and V in HSRN. So yeah, so that's how you prove this thing. So now continuing uh, our theory, next we are interested in this trace theory. So what we saw in the trace theory is that the if we have a function in Sobolev space, so let's say HSRN, then the Sobolev embedding actually will have its adjective onto h of s minus half. So half regularity is reduced uh, when we go to the boundary. So that much we have to lose. So the question is that for Sobolev spaces, we are actually able to reduce to the LP functions. So ultimately it is continuous in LP, and then it has actually we saw it has surjective onto a smaller subspace of LP. Now the argument we gave, the argument which you saw in the videos was that if we are considering to define a trace map, we defined a very specific map. We took the CC infinity function, and we show that the inequality holds, and then we use the density argument to prove the thing for all the HS functions. But the that was a particular map. So this gives us to a like raise to a question like that was a specific map, but there's a possibility that there exists some another map which is a continuous or a boundary linear functional which goes from LP to LP and LP of U to LP of boundary of U. But another type of so and if there is some another map which is defined in some another fashion, so this will give rise to another way to define the functions to define the boundary values. But like uh, we will see in the next question that that is not the case. We don't have a actually a uh, basically we don't have basically if we take a function in LP space, it's not possible to actually define a boundary linear functional from that LP space of the whole domain to the LP space of the boundary, such that that map turns out to be linear as well as bounded. So question 2. So it says that prove that there does not exist a bounded linear operator T from LP omega to let's say LPU to LP of boundary of U such that U is nothing but U restricted that U on the boundary whenever. So that was the thing we saw in the trace map which holds U belongs to the continuous function over all the U closure intersection LPU. Also, where what is U is a U be a bounded domain with the C1 boundary. So you guys know what do you mean by C1 boundary? So it's the bound. So it's a map. So I'm able to like for every point in the boundary, I'm able to have one map such that the upper half can be seen as a Q plus some Q, some upper version, some upper half of of a cube of Rn. So something like that. So So it's like again the trace map. So there's no such any trace map exists for the LP functions. So we need something at least more than so LP is like the H0. So H0 and we have seen the trace map has a domain of H of S minus half. So 0 minus half is negative. So that is we that much we need to have define the continuity of the trace map. So that is not there. So we have to show that if that is not there, we don't have any such bound linear map from LP to LP. So to prove this, we just need to show that if T is any map, uh, so T is any map, I have to show it is not continuous. So how do we show that? So we consider this sequence of functions u and x to be 1 minus distance of so 1 minus distance of x with the boundary of u, and then I multiply it by n so that then I take the positive part. So the positive part is helpful is like it is something like as if I take this to be my u, so anything on this is my boundary of u. So anything which is distance 1, so if anything outside that, it will take value 0. And whenever it has distance 1, so it will go increase from 0 to and go till 1 only. But since I want something which has which has LP uh, norm to tending towards 0, something like that. So what I will do, I will multiply it by n here. So instead of 1, it has distance 1 by n here. So anything outside 1 by n will have value 0. So since distance function is continuous, this implies u n x is continuous. Why that's the case? Because I know that since v plus can be seen as uh, v plus mod v whole divided by 2. So if distance is continuous, then the mod of then 1 minus distance is continuous. If that is continuous, then there's modulus is also continuous. And nothing v plus is nothing but the v plus mod v whole divided by 2. So that is continuous again. So we have v unx to be continuous and also but they're continuous on whole u bar. Also u is bounded. So what this basically implies, this implies that this un belongs to LP of u. So since they are continuous in u closure, so they are since they're continuous u closure, ultimately they are bounded. So they are bounded so they're in L infinity. Once they're in L infinity and over a bounded domain, they are in LP. So moreover, we can observe that u and x are lying between 0 and 1 only, since they are, I'm taking the positive part only, they are non-negative. And moreover, I am taking that this 1 minus n times distance, so they cannot exceed by 1 only. So distance is again a positive function, which is since then it's a non-negative function, so this has to be lying between 0 and 1 only. And one more thing, as n tends to infinity, what happens to u and x? So as n tends to infinity and x belongs to u and x so will tends to 0, or in fact it's eventually 0 only, as u and x is 0 for all n greater than equal to n naught, such that the distance of so distance of x with the boundary will be some quantity. So this will be some quantity. And what I want this quantity to be times n naught. And this whole thing so this whole thing has to be less than equal to, so this has to be actually greater than equal to 1, or distance of x with the boundary of u has to be greater than equal to 1 by n naught. Since distance is positive, I can find some n naught which is in a way such that this is greater than 1 by n naught. And once that is the case, we have this thing. And since that holds, we have this converges to 0 pointwise. So this converges to pointwise. Almost everywhere. Moreover, so then this converges pointwise almost everywhere. And then I have this one is integrable on u. So I can apply the dct here. Then by dominated convergence theorem, we have this uh, mod un whole is power of p of u. This thing, the limit of this thing is 0 only. So we have this thing. On the other hand, what do we have? We have this un. So LP norm at the boundary. So I know u's have distance on the boundary. So this is actually one only. So this thing is something the measure of my boundary, and not only that in major sense, this is actually in the uh, I would say in a surface measure. So this is a measure in the n-1 dimensional space. So this is a finite quantity, and that is not even zero since it is finite as well as also positive quantity. Hence, what do we have? We have the norm of TUN and the norm of UN. So UN has LP norm over U, and this will have LP norm of boundary over U. And this we know this is some constant. So let's say this is nothing but the UN. This is UN at boundary only. So this is just and this is UN at LPU. And this thing we know since above thing has some positive constant and the denominator is something which goes to zero. So this whole thing goes to infinity as n tends to infinity. This implies P will not be bounded because if there is some linear operator, then this ratio has to be bounded. So no such P exists. So next, what we like to do. So after this trace theory, we are interested in solving questions which actually the variational formulation of partial differential equations. So we're interested in solving that type of questions. So next question is like these are actually nice applications of these Lax-Milgram lemmas only. So so let us consider this question. So so prove that here exists a unique V naught in H101 such that U0 is nothing but, so it says H101, so it's continuously maintained in continuous functions. So we have this pointwise notion of functions. So U not U at 0 makes sense. Is integration of 0 to 1 U dash V dash V naught dash U time V naught. So this thing holds for all V in for all U in H101. So this is we have show that V naught is the uh, so we have to show this. So this holds, and we will do something more about this later. So solution. So we can see right hand side seems like a bilinear form. So first of all, let us prove that this right hand side, if we define t, let t define from h1 to rs, t of u to be u at 0. Then t is linear. Moreover, since we know that this h1 0 is continuously embedded in this L infinity space, we know that this mod u naught is nothing but less than equal to the L infinity of 0, 1, and that is again less than equal to some constant time, the h101 norm. So since that is the case, we have this t is linear, the uh, t is in the dual of h1, t is a bounded linear functional on h101. Also, let a from h1, sorry, let a from h101 cross to h1 cross 01 to r. We are mapping defined as h1 of uv as integration from 0 to 1 u dash v dash plus u times v. First, clearly, this mapping A is a bilinear map on h101 cross h101. Second thing, we have this to be symmetric, so A of uv is nothing but A of vu, thus A is symmetric. Then we have to answer AUV, the modulus. This is less than equal to 0 to 1 mod of u dash v dash plus 0 to 1 mod uv, and then by Cauchy's cos is the L2 norms are here. This comes from the Cauchy's cos. And finally, this u dash as whole thing can be written as less than the h1 norm of 0 times the h1 norm of v The same thing goes for the right hand side. So I can write a 2 here. So what this gives me a to b. A is a continuous. Finally, we need to see the H elliptic of the cohesivity. So H elliptic, or we also known as cohesive. I consider AUU. So this is nothing but is integration 0 to 1 mod u dash square plus u square. So this is nothing but my uh, H101 norm of u square. So that's the that we have here, and I know this thing actually goes to infinity as my norm u H101 goes to infinity. Thus AUU thus A is cohesive. A the Lax-Milgram lemma. What do we have here? We have here is that uh, for t there exists v naught in H101 such that a of u comma v naught is nothing but t of u, and that holds for all u in H101. But what this implies? This implies nothing but the integration of 0 to 1 u dash v naught dash plus uv is equal to nothing but u naught. So this is something which we wanted to just an application of Lax-Milgram lemma, right? So let's have another question. So another question is something which in here we are getting the cohesivity to be directly, but that is not always the case here. So since that is not always the case, so we'll have one question where we have to we have to use some more machinery, or not machinery, but some more techniques to finally get the cohesivity. So based on that, so we have another question. So let I to be equal to the interval 0 to 2, and v is equal to h1I. Consider the bilinear form is given as AU integration from 0 to 2 u dash t v dash t dt plus integration from 0 to 1 ut dt integration from 0 to 1 vt dt. So prove that AU is a continuous symmetric bilinear form with AUU equal to 0 implies U equal to 0, and then using this proof that A is coefficient as well. So it is, we have to show this is symmetric. So symmetry follows directly. So it's nothing in that. We have to show continuity next. So I consider mod of AUV. So one thing is less than equal to 0 to 2. Mod of U dash T, mod of V dash T, dt plus 0 to 1, mod UT, dt multiplied by integration 0 to 1, mod VT, dt. So now we can apply the Cauchy's cause in the first inequality, first integration, integral. So by Cauchy's cause, this is 0 to t u dash t square dt. So we have just done this. This is again 0 to 2 mod v dash t square dt whole power half, plus here we can use again the this is an positive integral, so this whole can be written as integration, and then using the Cauchy's cause 0 to 1 mod u dash t whole square dt whole power half, and then there will be integration with respect to 1, but that is 1 only, so I am not writing that. And then I can write this as whole thing to be 0 to u dash t square whole power half 0 to 2 mod vt square dt whole power half, and then I can take 0 to 2 here because of the positivity of the integrands. Once that's the case, whole thing is nothing but less than equal to the twice of h1 norm of u. Yes. So this gives continuity. So next, what do we need to prove? We need to prove that AU equal to 0 implies AU is equal to 0. So let AU equal to 0. This will imply that integration of 0 to 2 mod u dash t So u belongs to h1 of 0 to 2 dt plus integration of square 0 to 1 ut dt whole square equals to 0. When that is the case, it will imply the whole integration 0 to 2, integration 0 to 2 of u dash t whole square dt, since both are non-negative terms. So we have this 0 to 1 ut equal to 0. So since I have this my u dash t integration to be 0, and since u is again continuous, so because again of the embedding, so this point-wise makes sense. So this implies that u dash t has to be equal to 0 almost everywhere. And once that's the case, this implies that u has to be identical to constant almost everywhere. But this will imply this thing, so that this is just u only, ut. So integration of 0 to 1, c dt equal to 0. But that implies c has to be 0 only. So thus, u is identically equal to 0 almost everywhere. But since u has a continuous representative, so we can take u equal to 0 everywhere. U is identical to 0. Since h1 of 0 1 is again embedded in continuous functions. So we have this thing. Finally, we need the u to be cohesive. So we can see that cohesivity is not directly available because we have this thing not to be a norm. So this is not a norm. This thing is not a norm. So the cohesivity is not directly readily available. But we can prove the cohesivity in this case. And how do we do that? We use the contradiction argument to prove that this is cohesive. So on contrary, assume that A is not cohesive. So what will happen when A is not cohesive? Then there exists a sequence un in h1 of 0 to such that A of un comma un that goes to 0 and un is equal to h1 of has to be 1. So this is the same as saying the ratio of a un comma un whole divided by the norm of un that is not tending towards infinity. So this is the same thing. So this we can construct one such sequence. So what is a un? So a un comma un is nothing but integration 0 to 2 integration 0 to 2 mod of u dash un dash t whole square dt plus integration of 0 to 1 unt dt whole square. So this is my whole un. So this whole thing goes to 0. And sorry, so I have sorry, this has to be 1 only. Now as un is bounded in h1I, so then we have this thing. Then there exists a subsequence unk such that U and K converges weakly to some U in H1I, and U and K converges strongly to U in L2I by compact embedding. So this we saw in earlier lectures. So since this converges strongly in L2, this is also implies since I which is 0 to 2, this has a measure to be finite. What this implies? This implies that U and K converges strongly to U in L1I as well. Right, and moreover, by weak semi-continuity, we have integration of I of U dash integration of U dash square to be less than the limit of integration of I of U n dash square, and moreover we have this will imply integration of I of U dash square plus integration of 0 to 1 U, since because of strong convergence, 0 to 1 whole square has to be less than limit of integration of I of U n dash whole square plus 0 to 1 U n whole square. And I know this whole thing right hand side goes to 0. What this basically implies, this implies AUU has to be 0 because this is also non-negative. And once that is the case, we have proved that AU is 0 implies what that implies. This implies U has to be 0 only. But since U is 0, and moreover, but we know that U and K has H1 norm or 0 to norm to be equal to 1. Right. So what this implies? This implies what this implies? This implies that uh, this implies that we have this integration of I of U and K dash whole square, integration of I of U and K whole square equal to 1, right? And so A of U and K is nothing but integration of I of U and K dash whole square plus integration of 0 to 1 U and K whole square. And this can be written as integrate this whole thing. Now the U and K dash thing can be written as 1 minus integration of I of U and K square plus 0 to 1 U and K whole to power 2, but this goes to 1 by the strong convergence. Strong convergence of U and K to U in L2 as well as L1. So this implies A of UNK goes to 1 as k tends to infinity. And but we assumed that a of un goes to 0. So we have a contradiction. We have a contradiction. Thus, A is cohesive. Okay. So next, what we would like to see is that the minimization of a functional over a convex closed set is possible in a reflexive space, but if you try to characterize a reflexive space with the help of this criteria, then this is not true. So it's only a one way that reflexive implies we have a minima, but converse is not true, and that exactly what we'd like to see in the next question. So let's start. So we denote E with the space L1 intersection L2 are equipped with the norm the L1 norm plus the L2 norm. So first thing which we like to prove is that check that E is a Banach space. And then the second part we have let fx to be equal to f1 plus f2 with f1 lying in L infinity of E. So L infinity of R and f2 in L2 of R. Check that the mapping U goes to integration of R of fx dx is a continuous linear functional on E. So to prove it to be Banach space, first of all we try with the so we take a Cauchy sequence and we show this is convergent in E in the norm with respect to E. So what this will imply that U and Cauchy L1R as well as in L2R. So this comes from like the definition of the norm E, but L1 and L2 both are Banach. Ispanak. But this implies U and K. So UN converges to U in L1R for some in L1R. Similarly, we have as L2R is a Banach space 2. This implies that UN converges to some V in L2R for some V in L2R. So, what we'd like to, but we need to show this UN we have to be equal. We also know one thing, since UN converges to U in L1R, this implies that UNX converges to UX almost everywhere. Similarly, we have UNX converges to VX almost everywhere. But since we have this pointer convergence to be equal, this implies that UX has to be equal to VX almost everywhere. And thus, what do we have? We have UN converges to U in E. So now part 2, if T is a mapping from, let's say, E to R defined as T of F to be integration of R fx dx, fx ux dx, where fx is equal to fnx plus 2x. We have f1 in L infinity, and this is in L2 of R. So I consider the mod of Tf, and this is written as fnx ux. By the triangle inequality, we can write this. And then using the Helder inequality, so since f1 is in L1, L infinity, so I can use this by Helder inequality, the one norm of u into the L infinity norm of f1. Likewise, it again using the Helder inequality, we have this thing. Right. So next, this is finally less than equal to the, then one norm is less than the E norm. So this is can be written as this thing, and this actually will imply that T is a continuous linear function. So now part of the question is, let alpha between 0.5, check that the mapping u goes to ux whole divided by mod x for alpha dx is a continuous linear functional on E. So it's like it this actually follows directly from the part one. You can see that I can write this thing as characteristic of mod x greater than 1 and by mod x alpha plus characteristic of mod x less than equal to 1 and upon mod x square of alpha. Right. So this I write as f1 plus f2. Clearly we have f1 is in L infinity of r, and if we try to integrate taking the L2 norm of f1, so this is turns out to be mod x less than equal to 1 upon mod x raised to power of 2 alpha, which is nothing but twice of integration of 0 to 1 upon x raised to power of 2 alpha, and this is finite since my alpha lie between 0 and half. Thus we have our result. Next we consider a set K, which is a subset of E, such that I'm taking all those functions which are non-negative on R and integral value to be less than equal to 1. It's like a unit ball, sort of unit ball or L1 unit ball in E, and we check that K is a closed convex subset of E solution. So if UN converges to U in E, then we know that UNX converges to UX almost everywhere. And also we know that the UNX are greater than equal to. So this will imply that UX are greater than equal to 0 almost everywhere. So this again follows. So we can take a set even like we can take f1 to all those points where u1 is not non-negative or u1 is negative, then I can take the set f2 to be that where my u2 is negative, and I take the union and that again have a measure 0. Ultimately this will give me that ux is non-negative almost every. Moreover, we can use Fatah lemma to imply that integration of ux, since my these ux are all non-negative, so I can invoke again Fatah's lemma. So we have this thing to be less than equal to the lim info, then tending to infinity of integration of u and x. But this thing I know is all are less than 1, so lim inf is also less than equal to 1. And prove that thus u is closed. Moreover, convexity of k is trivial. So we can just directly check convexity by taking lambda 1 times u1 plus 1 plus lambda 2 1 minus lambda times u2, and then non-negativity and then this integrity are like very easy to, just by definition we can show that. So next part, let un be a sequence in this K and let U to be L2 of R be such that the UNs converges weakly to U in L2R. Check that U is in K and prove that the integral over R of this 1 upon mod x plus alpha UNX dx, this converges to integration of R 1 over mod x raised to alpha UX dx. So to prove U2 in K, I have to show that U is non-negative and the integral of U is less than equal to 1. And then also we need to show that U is in L1, so then it will be finally in E. So let me write this whole thing out. To show U in K, we need to show U to be non-negative almost everywhere, and the integration of Ux dx where R has to be less than 1, and then C is U has to be L1 of R. So consider to be this K tilde as all those U in L2. So let me not write U, let me write this. All those W in L2 of R is that W is non-negative almost everywhere. Is non-negative almost everywhere. So clearly K tilde is closed and convex in L2 of R, and thus I can see that K is weakly closed in L2R. But this implies that U belongs to K tilde, and thus we have U is non-negative almost everywhere. So once we have this, and so we are so once we have this, so part A is done. So next we are interested in showing that the integral of U has to be less than equal to 1. So I already know that UNs has integration to be less than equal to 1. So we'll use this. The U also has integral value to be less than equal to 1. So so for any measurable set A is that the measure of A is finite, we have the characteristic of A to win L2 of R. And since UN converges to U weakly in L2R, this implies the integration of chi a UN R goes to the chi a of U R. Right, so this implies the integration of A over A of UN converges to integration of A over U almost as n tends to infinity. But we know the integration of A of UN, since these UNs are in K, so they are non-negative, so they are has to be less than equal to UN over whole integration of all over R, and that is less than equal to 1. This will imply so that integration of A of U has to be less than equal to 1 for any measurable set A with measure of A has to be less than equal to has to be finite. So if we take in particular, if we take A to be the set of uh, minus K to K, where K is a natural number, so we can take this and letting K tending to infinity, we have integration of R of U is less than equal to 1. So once that is there and also U to be non-negative, this whole implies that U is in element of R as well. So this is just a byproduct. And finally, we have this thing that U is finally in E only. So and that is where this eventually implies that U actually lies in K only. And next, what we want to prove now this integration converges to this. So this converges to this thing. So now consider integration of R of UN upon mod x per alpha minus integration of R of U upon mod x per alpha. So one can be written as integration of R of 1 upon mod x per alpha into UN minus U. Finally, what we can do, we can divide this region into two parts when mod x is greater than n, 1 upon mod x alpha UN minus U, and one we can do when mod x greater than n, UN minus U. What this implies? This implies the integration of the modulus of this thing can be estimated with these two differences, these two sums, and the first sum is actually can be found above ms per alpha. We have this thing, and the final one is this, and also both are. This has to be mod x less than equal to n. And here I can use the Helder inequality in the second thing. Or we don't even need the Helder, we can even use this thing. We can take this to be, can write this as in a more better form. We can write this as integration of R characteristic of mod x less than equal to m whole divided by mod x to the power alpha into un minus u. And finally, since un belongs un and eu are all belonging to k, we can write the whole this thing as m raised to the power alpha into 1 plus 1 whole integration of into r characteristic of mod x less than equal to m whole divided by mod x raised to the power alpha into un minus u. We know that this belongs to L2 of R. So whole of this thing converges to 2 upon m raised to the power alpha as n tends to infinity for all m positive. What we can do, we can take m also tending towards 0 to conclude our result. So this will give that this actually converges to this thing. Now we consider finally considering the function k defined for every q in E by we define a functional ju integration over r q square x dx minus integration of r of ux whole divided by mod x raised to the power of alpha dx. Check that there is a constant c such that ju is bounded below for all u in by this k, this compact convex set. So how do we do that? So note that integration of r of ux mod x raised to the power of alpha dx again can be broken down as mod x less than 1 ux mod x raised to the power of alpha plus integration of mod x greater than or equal to 1 ux whole divided by x raised to the power of alpha dx. And then we can apply Helder or Cauchy's inequality to get here that integration of r of mod ux square whole is power of half and then mod x less than 1 upon mod x is power of 2 alpha whole is power of half, and then this is actually can be less than 1 and then integration of mod x greater than or equal to 1 ux dx for u belonging to k. So k u belongs to k. Now since u belongs to k, we will ultimately have this u L2 norm the half power. It will be some constant, so let's take this constant to be some, let's say, some m, and then this thing I know is less than equal to 1. So less than equal to 1, so I can call this by this thing. So what do we have here? We have j of u is nothing but the L2 norm of u minus, so it is greater than actually by 1 plus some constant m L2 of half. So this thing actually is a, if you see, it's like a square polynomial in square root of norm u of L2, and thus bounded below. So this proves that this j is bounded below. So next, what we're interested in is that if we take m to be the infimum of, so I can define this infimum, which is well defined now, over k of ju. Now let un be a sequence in k such that j of un converges to m. Prove that un of e is bounded. So that's the first step. One that we are anyhow getting the boundedness of our sequence un in E. How do we see that? We know that the j of un since converges to m, j1 is bounded. Also, we have this j of un is greater than equal to the norm of un. Oh, sorry, actually it's did I have a mistake here? It has to be square here and just a normal norm here. It's has to be un square minus 1 minus m times un, and again the L2 norm we are taking. We have this thing. Since J1 is bounded, what this implies? This implies all of this un L2 square minus 1 minus m un L2 has to be bounded by some m1 or some m1 in. But what this implies that un L2 whole square has to be less than equal to m1 plus 1 plus m times un L2 norm of R. So this forces our un norm of u L2 to be bounded. If it's not bounded, if it's unbounded, there exists a subsequence that un L2 norm square will go to infinity, and this will actually contradict the previous inequality. So this gives the boundedness of u L2 norm. Finally, since we know that uh, mod un s less than equal to, since what do we know about this now uns are in k, right? So this formula uns are greater than equal to 0 and uns are already have this type of thing to be true that the L1 norm is less than or equal to 1. So this actually just implies that UN L1 norm is less than 1. So we have UN L1 is also bounded. So eventually this will imply UN is bounded also. This. So next final thing which we want to know is that U and K be a subsequence such that U and K converges weakly to U in L2R. So this is possible because L2 is the reflexive space, so every bounded sequence will have a convergent, weakly convergent subsequence. What do you want to prove that? Prove that J of U is actually M only. So the minimum is actually attained. So to show this, since U and K converges to weakly to U in L2R, then from part 4, what do we have? We have U and K whole square x whole divided mod x square of alpha that goes to, it's not square, so it's just U and K goes to ux mod x raised to the power of alpha as k tends to infinity. So this comes from part 4. Moreover, from the weak convergence, we have this low semi-conductivity property. So this is that the two norm of U has to be less than equal to lim of del 2 norm of K, and thus we have integration of U square of all of R minus, since U is also belongs to K, so this has to be less than equal to this. M has to be less than equal to this thing, the value of Ju, since U belongs to K, and this is more Ux whole divided by mod x raised to power alpha over R, so less than equal to lim of J of, I would say, just U and K. This is just M only, and what this finally implied, this implies that J of U and J of U is nothing but J of U is M only, so the minimum is achieved. But as we see, the final thing, the goal of our question is this: we reached that show that he is not reflexive. So we prove this by contradiction. On contrary, if he is reflexive, I take even to be characteristic of n to n plus 1. So this is a sequence which is bounded in E. One can check directly. So this will imply it will have a U and K will converges weakly to U in E So we'll have a weak convergence. So in particular, we have integration of u and k into f over this converges to integration of r uf all r for all f in CCR, so completely coupled functions. So in fact, more is true. In fact, I can say all those eligibility functions plus f has compact support. But I know that this U and K have supports which are tending towards infinity. So what this eventually implies, we can show that the integration of fu has to be 0 for all f in L infinity plus the support of f is compact. But once that is there, this actually implies one can show that U has to be 0 almost everywhere. But we take f to be just identically to 1, this will imply the integration of u has to be equal to 1 because the integration of is nothing but the limit of k tending to infinity of f times u and k over r, which is nothing but the limit of k tending to infinity of integration of r of characteristic of nk2 nk plus 1. So this is 1 only, and this is a contradiction. This implies E is not reflexive. So finally, we have a sequence, so a space which is not reflexive, but still the minimum is achieved. So the if and only if characterization is not there. And with this, I end this session. Thank you.